Thanks for giving me the opportunity to show you what makes Tec-Ease training materials your best choice for your GD&T training. Most training will teach you the rules, terms, and definitions of dimensioning and tolerancing standards, but at the end of the training the students are unsure about how to use what they've learned. That's where the GD&T hierarchy comes in. We are the only ones that use this dynamic tool to instill how GD&T may be used effectively. Our design engineering background has allowed us to include real case studies of GD&T applications, not a bunch of blocks with holes in them, those Swiss cheese parts. Because of our educational background, we know how to keep the learner interested in the material by using both sides of the brain and use techniques like spiraling to assure retention of the concepts. Now let me show you some of the samples of our materials.
Like I said, we use the GD&T hierarchy. In fact, that's the title of our textbook. We use several different techniques, including flowcharts, and here's a little animation, to illustrate the hierarchy. We point out that the geometric controls are tools in your toolbox. But like any tools, if you don't know how to use them, they're not going to do you any good. So we tell people what to go for first. Once they've established their origins of measurement by using datum features to establish their datum reference frame, then you open up the toolbox and we find that location is on top. You must locate other features relative to these origins of measurement. And then, only if necessary, might you go further into the toolbox to pull out the orientation tolerances. You got them for free with location, so the only reason to get the actual orientation tolerances is to tweak what you already have controlled. And once in a while you have to dig way down into the toolbox for the form controls, and yeah, we put profile of a line down there because we get form control for free with size tolerances, many times with locating tolerances like profile, and with the orientation tolerances on surfaces. So it's rare that you need to dig way down into the toolbox. This is just one example of the analogies that we use to make GD&T clear. You'll notice down at the lower right corner of the slide is the page number that this would relate to. It makes it easier for the folks to follow. Throughout our training materials in our PowerPoint, we use real application. This is an example of a fuel valve. It's a real fuel valve. And we show the importance of selecting your datum features in an order that reduces the number of tolerances in your assembly. And here's an example of a tolerance analysis that we illustrate. Included with the PowerPoint are speaker notes so that you know what we think ought to be said with each one of the slides. Of course, you can customize that all you want. As I said, we use several case studies. Here's one of a roller bearing. This was a brand new roller bearing as shipped. These two rollers were right next to one another. And we show how Rule 1, if used correctly, would have picked this problem up, so it wouldn't have been shipped to the customer. This is an overlay that the students have that they get to work with, and first we calibrate our ring gauge at 20 millimeters and our anvil mic and our 2-point micrometer. We then bring in that 5-lobe part, which is very common in centerless grinding, 5 and 7-lobe parts, even 3. And we show how, no matter how you mic that bearing, you could not detect the lobing effect. And even if you put it in the anvil mic or tri-mic, as you rotate it, the mic would not change. But if they had followed Rule 1 and checked the perfect form at the maximum material condition, they would have found that that had a lobing problem. So a lot of use of color in 3D. We stick to the terms that are found in the Y14.5 standard. We're sticklers about having the terms used properly. We use a lot of analogies and animations to explain things like the 6 degrees of freedom. We point out that an airplane in space, as with all parts, has 6 degrees of freedom. The 3 tudes, latitude, longitude, and altitude. And the other 3 tudes, which are the attitudes of pitch, roll, and yaw, and how we use datum features on parts to constrain some or all of these degrees of freedom. So then we walk through the various features on the part and we show what degrees of freedom remain. In this case, if I set this flat surface down on a surface plate. I still can translate in 2 directions and rotate, so I must have taken away the other 3 degrees of freedom, which would be 2 rotations and 1 translation. We like to, whenever possible, show examples of real inspection equipment, this being a surface plate. After we've introduced the concept, then we ask questions. Many of these questions are found in our workbook, as this one is, and we've supplemented with additional questions that are not found in the workbook. Because our PowerPoints can be customized, you have the option of skipping these if you have a very short amount of time to cover the work. We emphasize design intent, which is what the standards emphasize, and we show how by walking through assemblies and looking at the features that constrain the degrees of freedom, you can find the most efficient way to select your datum features. And then we show the resulting datum reference frame. Where a concept is a little tougher to understand, we make use of video. Here we're explaining how the datum shift that you can get when a max material boundary symbol is applied to a datum reference isn't really giving you a bonus, it's giving you a shift. In this case, you would get datum shift left-right, but not up-down. And to illustrate this, we used a hard gauge and a video, and we show how the gauge pin won't fit through this hole. Once we shift the part around on the gauge, there's the datum shift in that one direction, then we can get the part to be accepted by the gauge. We're not pushing gauging, but sometimes we use gauges to illustrate a concept. It's easier to visualize that way. Another difficult concept for folks to grasp sometimes is simultaneous requirements, so we use animation to illustrate controlling the relationship between this key seat and the pair of flats on the other end of the shaft. For some design requirements, where I have a cam, for instance, on one end of the shaft and a timing gear on the other, I want simultaneous requirements, which is the default of the standard. Since these features reference datum feature A, they become a pattern. Simultaneous requirements. And if I don't want that pattern, I must say separate requirements. In this application, now a friction disc is going onto the pair of flats, and a V pulley is making use of the key seat. So here I really don't worry about the orientation, and I would say separate requirements. So a part like this would be acceptable. Here's a couple more examples where we're using real parts to illustrate a concept. This is the one for customized datum reference frameworks, which is difficult for people to grasp. Here's another example with a tool holder and how customizing degrees of freedom allows us to change where the origin is from out here at the vertex of the cone to this surface, which is much easier to find. Using 3D and color really makes it easy to explain things like the various tolerance zones. So we illustrate all of the tolerance zones in 3D. We also illustrate sample verification. And in this case, talking about position, we use the color in 3D to explain the difference between the surface interpretation and the axis or center plane interpretation. Here's a dynamic tolerancing diagram where we put size along the x-axis and the geometric control along the y, and point out that this position tolerance applies at the smallest hole, which would be at 11.8, and as that hole gets bigger, you get additional tolerance because of the maximum material condition modifier. We feel that these dynamic tolerancing diagrams really help the learner to grasp the concept of max material and least material condition, and to point out that there is a boundary that is being protected by this position callout. It's known as the virtual condition boundary, or the inner boundary, or more recently the max material boundary. If we were to build a hard gauge, then we would build the hard gauge at that 11.5, adjusting for gauge tolerance and wear allowance, of course. And so a hard gauge with sliding pins and a sliding block might look something like this, where we first establish our datum reference frame and then verify that the boundaries haven't been violated by the part. And then here's one of the examples of an exercise that the students need to work on to create their own dynamic tolerancing diagram. And they have the opportunity to calculate gauge sizes. This animation shows how concentricity and circularity or cylindricity are both controlled by the two runouts. All of the animations that you've seen in this presentation are exactly as they appear when you run the PowerPoint slides.
Another strength of Tec-Ease is our customer service. Wendy or Dave will be glad to help you determine which of our products will best fit your needs. Anytime you have a technical question, I encourage you to give me a call or send an email. There won't be a charge for the question. You'll find over 150 free tips on GD&T indexed on our website. We believe in helping promote the GD&T standards and helping folks get it right the first time. Thanks for taking some of your valuable time to check us out. I look forward to working with you in the future.